Good morning, everyone. Today I'm presenting a paper titled Sum Rate and Fairness Analysis of RSMA, SDMA, and NOMA in MISO Downlink under Perfect and Imperfect CSIT. This work compasses three multiple access techniques, which are RSMA, SDMA, and NOMA, to evaluate which performs better in terms of sum rate, fairness, and robustness when channel information is either perfect or imperfect. Let's get into the introduction. As wireless networks continue to evolve towards 5G advanced and 6G, supporting more users with higher data rates has become a major challenge. Existing techniques such as SDMA use spatial multiplexing, while NOMA uses power domain multiplexing with successive interference cancellation. However, both techniques experience performance degradation when the transmitter has inaccurate channel information. To overcome this limitation, RSMA splits each user's message into common and private parts, allowing some interference to be decoded and the remaining interference to be treated as noise. This makes RSMA more flexible and robust. The main contributions of our work are fourfold. First, we developed a practical one-layer RSMA framework using regularized zero forcing or RZF together with adaptive power allocation. Second, we compared RSMA, SDMA and NOMA under both perfect and imperfect CIST using Monte Carlo simulations. Third, we evaluated the achievable degrees of freedom or DOF under different CSIT qualities. Finally, we analyzed maximum minimum fairness, showing that RSMA provides better fairness than the other two schemes. Previous research has shown that RSMA provides a good balance between decoding interference and treating interference as noise. Most earlier works rely on optimization techniques such as WMMSE, which are computationally expensive. In our work, we instead use a low complexity implementation based on RZF pre-coding and adaptive power allocation. Our system consists of a base station with 4 transmit antennas serving 4 single antenna users, and we compare all 3 multiple access schemes under the same conditions. This slide explains the communication model. We consider a MISO downlink channel where the transmitter communicates with 4 users. Since practical systems cannot estimate the channel perfectly, we introduce an imperfectly CSIT model where estimation errors depend on a parameter called alpha. When alpha equals 1, channel estimation is nearly perfect. Lower values represent more realistic situations with higher estimation errors. This allows us to evaluate how robust each multiple access scheme is. Reaching approximately 35 bps per hertz at high SNR. NOMA performs significantly worse because it cannot fully exploit spatial multiplexing. This shows that when channel information is perfect, SDMA already performs very well, leaving little room for RSMA to improve. These graphs show the results when channel information is imperfect. Here, RSMA consistently outperforms both SDMA and NOMA, especially at higher SNR values. The common stream in RSMA helps reduce the effect of residual interference caused by channel estimation errors. As the quality of CSIT improves from alpha equals 0.5 to 0.6, the performance advantage of RSMA becomes even more noticeable. These graphs compare maximum minimum fairness, which represents the performance of the weakest user. RSMA achieves the highest fairness while NOMA quickly reaches a saturation point. SDMA performs better than NOMA but still remains below RSMA. We also observe that our practical implementation achieves slightly lower degrees of freedom than the theoretical limit because we use a heuristic power allocation instead of optimization techniques such as WMMSE. However, the overall performance remains the same, with RSMA providing the best overall performance. So to conclude, our study compared RSMA, SDMA and NOMA under both perfect and imperfect CSIT conditions. We found that RSMA performs slightly similar to SDMA when channel information is perfect, but clearly outperforms both SDMA and NOMA when channel estimation is imperfect. It also provides better fairness and stronger robustness against interference. Future work will focus on optimization based beam forcing techniques such as WMMSE to further improve performance. Thank you for your attention. I would be happy to answer any questions. You can drop down in the comment section. Thank you so much.